Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 4.6, day 1, entitled Modeling with Exponential and Logarithmic Functions. And remember, with modeling, that means we're going to be doing some application word problems. So today we're just going to focus on exponential growth, and then, two types of exponential growth, and then radioactive decay. And we've already seen how exponential functions can model a lot of different situations like population growth or radioactive decay. So now we're going to talk about some instances where logarithmic functions can be used to model real life situations like loudness, earthquakes, etc. So the first application we're going to talk about is doubling time for exponential growth. And suppose here, in this case, we're starting with a single bacterium, and it divides every hour. So after an hour, you'd have 2. After 2 hours, you'd have 4. After 3 hours, you'd have 8, etc., etc. So you can see in the picture here, they have the time listed across the bottom, and then they have the little bacterium drawn in the bowl. Okay, and the model that we're using here would be 2 to some power, because if it's doubling, 2 to the first would be 2, 2 to the second after 2 hours would be 4, 2 to the third after 3 hours would be 8. Okay, and we can adjust that formula a little bit, and we can say, okay, what if instead of starting with 1, what if we started with 10 bacteria? Well, then you just put a 10 in front of your function. So 10 times 2 to the t, okay? And t would stand for time. Now, you could adjust that to really be any number of bacterium, too. It doesn't just have to be 10. And you could adjust your time, too, because sometimes stuff doesn't double every hour. Sometimes it takes maybe 3 hours, or maybe it takes a half hour. Maybe it takes an hour and 20 minutes, okay? So the formula that we're going to be working with is down here at the bottom of the slide in this little box. Okay, and we're going to have n sub 0, which represents the amount of bacteria that you're starting with. It's always going to be 2 to some power because this is for a doubling situation. And then we're going to have t divided by a. So t is going to be your time, and then a is going to be how many times it doubles, or the doubling time, how long it takes to double. So in this case up here where they're explaining it, it says the bacteria doubles every 3 hours. So they took t and divided it by 3. So A is going to be the doubling time. So we're going to use that equation here for example 1. And example 1 has 3 parts to it. It has an A and a B and a C. And here we have a bacterium that, under ideal conditions, doubles every 3 hours. And initially, we're starting with 1,000 bacteria in a colony. So we want to write an equation to model this situation. So originally, we had n of t, that's the number of bacteria, and then that's our initial bacteria, n of 0, and it's doubling, so it's going to be 2 to the t over a. So that's the formula that we saw on the previous slide. And now we're just going to adjust it for our situation. Okay, we're still finding the number of bacteria after a certain amount of time, so we're still going to have n of t, but we're starting with 1,000, so that's n sub 0, that's our initial amount, and we're doubling. We don't know the time, that's what we would want to put in, but it's doubling every 3 hours, so we're going to have t divided by 3. So that would be our equation that we would use then. And once they gave us a time, then we could figure out how many bacteria we would have after that time. Or they could give us the amount of bacteria, and we could tell them how long it would take to get that amount. So that's what we're going to do in part B and C. Okay, so how many bacteria are in the colony after 15 hours? So we're going to find n of t, the number of bacteria after a certain amount of time. We started with 1,000, and then 2 to the, now our time is 15 over 3. So I'm using that equation from part A, and I'm just substituting in the 15 for the t. Okay, so really we're finding n, n of 15 is really what we're substituting in there. So 1,000, and then 15 divided by 3 would be to the 5. So here when you do this, you want to do 2 to the 5th, which is going to be 32 times 1,000 will get you 32,000 bacteria. So if you had to answer that in a sentence, you could say after 15 hours there will be 32,000 bacteria. Okay, and then part C just reverses the process. It says when will the bacteria count reach 100,000? So now we're finding the t, we're finding time, but they give us the amount after that certain amount of time. They give us the 100,000. We're still starting with 1,000, and we're still doubling, but now we're finding t. So this is where the logarithms are going to come in to help us solve this, because we're solving for t, and it's in the exponent. So we're going to need to take the log of both sides so we can drop that exponent down out in front. But first I have to get that power, that 2 to the t divided by 3, I have to get that by itself. So I'm going to divide by the 1,000. So that'll get me 100. Remember, we're just canceling off our zeros here. So that's going to get me 100. And then if I take the log of both sides, I'll have log of 100. And then this t divided by 3 is going to drop down in front. And then I'll have log 2. So we're really doing 2 steps in 1 there. There's multiplication going on there. Okay, now if I'm trying to solve for t, t is being divided by 3 and multiplied by log 2. So I've got to undo both of those. So I'm going to multiply both sides by 3 now to get that dividing by 3 out of there. So I'll have 3 log 100 equals t log 2. And then I just have to divide by log 2. Okay. So t is going to equal whatever 3 times the log of 100 is, divided by the log of 2. And you should get about 19.93 hours. And again, if we needed to say that in a sentence, we could say after about 19.9 hours, the bacteria will reach 100,000. Okay, so these formulas that we're going to be working with, they're going to have exponents in them. You might need to use the logarithms in order to solve for a variable in the exponent. Now we're going to look at another type of exponential growth. This is just a relative growth rate. And in the past, we've used exponential functions that have a base of 2. That's pretty much just what we did for the doubling one. But sometimes things triple. So we could have a base of 3. Or they quadruple, so I could have a base of 4. Really, I could have a base of any number. I could even have a base of e. So now we're going to have an equation where we have a base of e. And we're going to get a model for relative growth rate. So this would be the growth of a population as a proportion of the population at any time. Okay, so that's this equation right here. Very similar to what we were using. We're still going to start with n sub 0. That's our initial population. The n of t is going to be the population after a certain amount of time. T is going to be time, and r is going to be our rate. But notice that we have e now for our base. Because population doesn't just grow at a certain time of day. Population is continuous. Okay? Babies are being born at all different times of the day. So it's constantly growing. So we want e to be used whenever we're in a continuous situation. Notice that formula is similar to the continuously compounded interest. That's where we had the PERT, where we had E, P times E to the RT. So any situation where you have a continuous growth, you want to have E in it. Okay, so this could be if we were dealing with either, in the past when we were doing the P times E to the RT, that was dealing with money. So that was an investment. Now we're dealing with a population, but either of those applications still work. Okay, so for example 3 here, we have a bacterium. An initial bacterium count on a culture is 500. And a biologist later makes a sample count of the bacteria and finds that the relative growth rate is 40% per hour. So again, we've got a part A and B and C and D for this one. So part A says find a function that models this situation, the number of bacteria after T hours. Okay, so on the slide we had n of t, the number after a certain amount of time, was equal to the initial amount, n sub 0, times e to the rt, the rate times time. So that was our standard formula. And now we're going to plug in what we have. We have 500 for our initial amount. We have our growth rate of 40%. So we'll have n of t equals 500 times e to the 0.4 t. Remember, I have to change 40% to a decimal, so I have to move the decimal to the left 2 places. So that's my equation that I would use then for this situation. So again, now we're going to find the estimated count of the bacteria after 10 hours. So we're going to use that equation that we just wrote, and we're going to substitute 10 into it. So we had 500 times e to the 0.4 times 10. And remember, you want to simplify this one step at a time. So do 0.4 times 10, that'll get you 4. Do e to the 4th, get an answer, and then multiply it by 500. And when you do that, you should get 27,299.08. So if we wanted to round it a little bit better, we'd have, 27,299 bacteria. Or I suppose you could round up. You could say you can't have 0.8 of a bacteria, so you could even say 27,300. That would be fine. So that was just basic substitution. Now we're going to reverse the process a little bit and find the time. So we're going to find when the bacteria will reach 80,000. So I'm going to put in 80,000 for my n of t. But now I'm going to be solving for t. I'm going to be solving for the time. So again, since I have that variable in the exponent, I'm going to have to do something to get that out of the exponent. But I have to get this base and the exponent by itself first. So this e to the 0.4t, I've got to get that by itself, so I have to divide by the 500 first. So 80,000 divided by 500, that'll be 160. And then I have e to the 0.4t. Now to get rid of the e, we're going to take the natural log of both sides. Okay, so the natural log and the e over here, they cancel. So now I have the natural log of 160 equals 0.4t. So to finish solving for t, I just have to divide by 0.4. So you should get about 12.69 hours. Okay, so that's very similar to what we did in our first example. We're using the formula both ways. But now we're going to take it a step further and we're going to graph that original function that we had. So if we go to y equals on our calculator and we type in 500 times e to the 0.4x in our calculator, we might also need to adjust our window before we can graph this. So we would want our x-min and our y-min to both be 0. It doesn't make much sense to have a negative amount of bacteria. And I just picked an x-max of 10 just to represent the first 10 hours. And then I don't know how big this is going to get in my first 10 hours, so I'm just kind of estimating a big number here. I'm going to put 30,000 in. You could look at your table of values too, and then adjust it on the window afterwards. But if we graph, we get that very slow, very gradual exponential function. Okay. And if we were going to actually graph this by hand, then we would want to go to our table of values, and we'd want to write down our first few values. Okay. So at t sub 0, we have 500, t sub 1, 2, 3, 4, 5, 6, etc. You could probably go down to the first 10. Or maybe do every other, do like 0, 2, 4, 6, 8, 10. But you see that at 10, it's already at 27,000. So this grows pretty fast. Okay. So I'll just put on here on the calculator. Oops. And we'll have to adjust our window. And then we'll need a table of values. Now here's the nice book graph of the function. But remember, if you needed to graph this on your own, you'd want to make a table of values, write down those values, and then graph. It's better to draw your own graph probably than to use graph paper for this one. Okay, and then the last thing we're going to talk about is radioactive decay. And radioactive decay is when a substance decays. And scientists call this half-life. Physicists express the rate of decay in terms of a half-life. So that basically means how long it takes for a certain amount of that element to decay halfway. So here we have radium-226, and its half-life is 1,600 years. So that's not very fast. So if you had 100 grams of that radium-226, after 1,600 years, you would have 50 grams of it. Okay. So we can write an equation for this, and we want to show that something is decaying and that it's got a half-life, so it's being divided in half and in half and in half. So we really want a 1/2 in our equation, or we can have a base of 2 and then make it to the -1 for an exponent. So that's why we have this base of 2 and then we have our negative here. Now we're still starting with our m sub 0, that's our initial amount. And we're not really doubling, we're halving, but it's 2 to the -1 instead of 1 over 2. And then we have t for time, and then h is the half-life. And that amount of time and that half-life, they have to be in the same units. So it has to be days or weeks or years. So they have to be the same. And then this would be similar to if we modeled it with E, we'd have m sub 0 times e to the RT. But we'd have to make that RT negative. So we need a negative in front of the R. And then they do something a little bit different then. If we're going to have something that's continuously decaying, we've got the E in there. And we're also going to rewrite the rate a little bit. We're going to rewrite the rate with a natural log. It'll be the natural log of 2 divided by h. And this has our explanation of how we do that and how we get that. So the equation that we're actually going to be using is this one, m sub 0 times e to the negative rt, but the rate is going to be the natural log of 2 divided by h, divided by that half-life. So they're not probably going to tell you the rate, they're just going to tell you the half-life. So then you have to find its rate, perhaps. So if we look at our next example, there we go, last example, example 6. Here we have polonium-210, has a half-life of 140 days, so that decays pretty fast. And suppose a sample of this substance has a mass of 300 milligrams. There's A, B, and C, and D parts to this, but in part A, they want us to find a function that models the mass remaining after T days. So just like our other examples, we're going to write an equation. We're going to use that function that we had on the previous slide, but I'm going to rewrite it a little bit. I'm going to have m sub 0 times e, but instead of the rate, I'm going to put in the negative natural log of 2 over h times t. I'm just going to put that right in. Now you could find the rate separately and then just plug in that number for the rate. That's fine too. But if we don't know what that number is, it's better to have the equation written like this with the negative natural log of 2 over h in there for the rate. So we know our initial amount. We had 300 milligrams of that sample substance. E is going to stay E. We're going to have the negative natural log of 2 over. Now our half-life is 140 days. So I'm going to put 140 in there times T. Now you'd have to make sure that your time is measured in days here. So you could use that equation, perfectly fine. Remember that we're dealing with time in days. And if you wanted to, you could do the negative natural log of 2 divided by 140 and actually get that decimal, which would be negative 0.00495. So if you wanted to put that into your equation, you could. So now it says find the mass remaining after 1 year. So again, remember we're dealing with days here. Our time is days. So 1 year is going to be 365. So I'm going to put 365 into my equation. So I'll have 300 times E. Now the negative natural log of 2 over 140, I calculated that already. That was over here. Okay. But I'll just leave negative natural log of 2 over 140 for now. And then our time is going to be 365. Now you want to simplify that. So you want to take the negative natural log of 2, divide it by 140, get an answer, which is over here, and then multiply that by the 365. So you should get e to the negative 1.807. And then you can do e to that power, get an answer, and then multiply by 300, and you should get about 49.24 milligrams. Oops, milligrams. And again, if you had to say that in a sentence, you could say, after a year, we will have about 49 milligrams left. Okay, part C and D. How long will it take for the sample to decay to a mass of 200 milligrams? So now we know M of T. We know that's 200. We have our 300 originally that we started with. Now, we're probably going to assume that this is going to be, how long will it take? Oh, we don't know our time, do we? Okay. So we still don't have the negative natural log of 2 over, now originally we had the 140 in there. So this part here, this exponent, the negative natural log of 2 divided by 140, that's that 0.00495. So I'm going to have, let's see, I need to take and divide by the 300 on both sides. And then I need to simplify that negative natural log as well. So I'm going to do 2 steps in one here. I'm going to divide by 300, so I'll get 0.67. And then this negative natural log of 2 divided by 140 is going to be negative 0.00495 times t. So now again, I'm trying to solve for t. I'm finding out how long I have to solve for t. So I'm going to have to take the log of both sides. Now I want to be a little smart here because if I take the log of both sides, I want to take the natural log so that it'll cancel out the e. So I'm going to take the natural log of 0.67. And then if I do the natural log of e, that's going to cancel and this stuff will drop down. And then all I have to do to solve for t is divide by that. So you should get about 80.9 days. Now again, do this one step at a time. Take the natural log of 0.67 and get an answer. Then divide by the negative 0.00495. And you could round that. You could say it's about 81 days if you would like to. And then part D says to find the answer to part C numerically and graphically. Remember, numerically means in a table of values. So again, we'd want to go to our graphing calculator and we would want to put in our equation. And we could put in our generic equation. We could put in the 300 times e to the, now I'm not going to put negative natural log of 2 divided by 8 or negative 2 or 2 divided by 140. I'm going to put in the decimal. Negative 0.00495 times x. Okay, so that would be my original equation. And it took 81 days for my answer in part C. How long will it take the sample to decay to a mass of 200? Now, originally, I started off with 300 as my sample. So if I'm going to adjust my window here, the original amount that I'm putting in is starting at 300. So I guess I could start there at 300. Let's go by a scale of 10 just to make it a little bit nicer. My Y max value, not really sure, but I know I've got to have 81 days, and I know I've got to have 200 as a high value. So 200, if I'm substituting that in, that's covered within this 0 to 300 range. And then my y's coming out, I need it to be at least 80. Maybe let's make this 100 and see what happens. And let's do a scale of 10, and we'll graph. Oops, off just a little bit. So let me go back at my y max. Let me make it a little bit bigger. Let's just go really big. Let's do 1,000. There we go. Okay, so that was way too big. So we'll go back just so it's more viewable. So let's just do 500. Oops. There we go. There, that's a little bit better graph. Now, if I'm trying to, for part D, if I'm trying to find the answer numerically and graphically, that means that I have to find out how long it will take for the sample to decrease to 200. So I could do a couple different things. I could look at my table of values. Now you notice here that my table of values are going down really, really slow. I'd have to arrow down a lot. Now we know I want my y value to be 200. I'm at 280. So you could, if you wanted to, adjust your table settings. Let's say we start at 0 and then we go every 10. And I can go back to my table. Okay, and now I can see if I scroll down. Okay, 80 is on there. And 201 is the value that they had. We had about 200. Okay, so you can show that it's in the table of values, or on your graph, you could always trace. Until my y value is about 200. Ooh. Something seems a little off here on this one. I have R and then theta. Oh, that's because I'm going the wrong direction. I'm getting too big. I'm going to get smaller. Oop, there's a little jump there. It goes like 2.9. Okay, not really a big fan of this trace feature right now. I don't know why. But you could trace it and you could find it on the graphing calculator. I think it's better to go to your table of values. It's more direct. And the book's graph looks like this. Okay, so they're starting at 300. It's gradually going down. You'd want to write down the table of values. And again, you could do like every 10 days. So you could go from 0 to 10, or you could do 0, 2, 4, 6, 8, 10, and then plot some of your points. But the point that has to be on there is 81 days and 200 for your output. So you have to, if this was a quiz or a test question and they wanted you to graph it, you'd have to write down your table of values as well. And then you'd have to graph it and you have to show where that point is on the graph. Make sure that point that you're putting in is on the graph. Okay, so these are a little bit more challenging, so there's not as many of them, but definitely practice these problems. Remember, the work is all done in the binder in the classroom, so this might be a good section that you want to take a look at some of those and see how the work is worked out. And if you have any questions, come on in and see me before school.